What's up, TubeUbers? It's Miss Sorensen, and I'm your host today for video 2, Distribution and Standard Deviation. I just can't wait to teach you all this, so let's get started. Let's talk about some vocabulary here. What is distribution? Distribution of a data set describes the values taken on by the variable and the frequency or the relative frequency of these values. For example, here is the distribution of SAT scores below. So what does this mean? This really means that 34.13% of people score in the 500 to 600 range, right? That means that there's a big chunk of people there. Versus if you look over here, the distribution is a lot lower here. Only 2.15% of people score from 700 to 800 points. And this is how it's distributed. What you can see here is that most people are scoring between 400 and 600. It's a huge chunk of people. Most people are centered at here. And there aren't many people scoring from 200 to 300 and from 700 to 800. Let's talk now a little bit more about the shapes of these distributions. So first we have the symmetric distribution. This is when both sides are more or less the same. They're symmetric. So when you fold vertically down the middle, if you were to fold right here, you would see that it would be the same on both sides. There's a bell-shaped curve, and that's also a type of symmetric distribution. And you know that that is when the center is mounded at the middle, and then you've got two sloping tails right here. So this would be a bell curve. Uniform distribution is when pretty much everyone is equal or approximately equal. So time waiting at the bus stop here, most people are waiting around 40 minutes here, right? It's almost everyone is exactly the same. Not exactly, but approximately equal. So this is called uniform distribution. Now I want to talk about left skewed or negative skewed. And this one I always get confused with, but honestly, you just have to think about what way are you pulling the tail. So it's which way you pull the tail. So here's a tail right here. I'm going to put a little, I don't know, fur on it. Which way would you take your hand and pull that? Here's my hand grabbing the tail, and I would be pulling it this way, meaning that this here is left skewed. And the question is really why though, because it looks like it should be called right skewed. Let me see if I can give you an example of why this is true. If this was left skewed, we'd have a data point right around here that was kind of an outlier, if you will. Like for example, we have maybe this is how much money we have in our pocket, $1, $77, 78, 80, 82, 85, 86. You can see that we are really, most of our values are high. So we'd have something like most people are on the right here. But we have one value, in this case 1, that pulls our data over here, right? So we'd still have to represent that on our frequency chart here with our curve on it. And the question is, why is that still called left skewed? Well, let's see if I can explain this. If I found the median of this data, okay, I'd have to cross out left, right, left, right, left, right. I'd be left with this one right here, and that's my median. Okay, so I'm going to label that right here. That's my median of 80. My mean, however, or my average, I'd add up all these values right here. I'd add up all these values, and I would divide by 7 because there's 7 terms. So if I do that, I get, real quickly, 489 divided by 7. That gives me a mean of 69.85. Well, where is that mean? It is to the left of the median. Okay, so basically what's happening is this mean is being pulled to the left. Why is it being pulled to the left? Because this 1 is kind of like an outlier and it brings it to the left. So if we were to kind of summarize why this is called left skewed, I would say that the mean is to the left of the median. How would I memorize it though? I would most definitely memorize it by saying, which way do we pull this tail? Here's my tail. I'm going to pull that straight to the left. So this is left skewed. And sometimes people call it negative skewed. All right, let's talk about right skewed. Why is this considered right skewed? Well, here's my tail right here, fluffy tail. And I'm taking my hand. Yeah, it's a nice hand. And I'm going to grab it and I'm going to pull it this way. So this one here is a right skewed. Now let me give you another example to persuade you. Let's say I have the data values 1, 2, 3, 3, 4, 5, and let's throw in a big one to make it right skewed. That would be 25. Right? The majority of our data is 1, 2, 3, 4, and 5 is majority of it's here. But then we have this outlier, this 25, which is all the way out here. All right, so let me find the median. Median is going to be this middle value of 3. And I'm just going to quickly add these all up. That gives me 43. I've got 7 terms, meaning that my average or my mean is actually 6.14. Well, what happens here? It looks like my median is 3, but my mean is pulled way to the right because of this outlier right here. So this is a 6.14. So why is this called right skew? Because my mean is to the right of my median. And the reason that is because the median is not impacted by that big number, but my mean, my average, is impacted by it because I have to count it in this value here. All right, now let's talk a little bit about variation. So variation describes how widely data values are spread out about the center of a distribution. So low variation means, yeah, there's some sort of a bell curve where most people are scoring here or are getting this type of time on a track race, but most everyone is relatively the same. Okay, versus moderate variation might be the state meet, where, yeah, there's some super fast runners, but most people, because they qualified for state, are around here. High variation might be something like a city run meet, where you've got people from college who are running really fast, and then maybe Miss Sorensen, who is running with her cats, has got a really bad time. So there's a huge difference in people's times or scores. So how would the variation of a 5K time be in a city race versus a state meet versus Olympics? So what I'd say here is the variation of a city race, well, that's everyone. Okay, a city race would be a much wider variation or a high variation. A state meet, probably moderate. Okay, and the Olympics, where everyone is relatively the same, within maybe 0.05, depending on the race, would be this low variation, where almost everyone is the same. All right, new topic here, and that's called standard deviation. How do I get this to go forward? Standard deviation shows the variation in the data. So if the data is close together, the standard deviation will be small. If the data is spread out, the standard deviation will be large. Here's the formula. So this letter right here, S, let me use a different color here. S obviously stands for sample in this case. And so we are going to talk about S almost exclusively because we can't go out and survey the entire population. All right, so if you see this letter S, and we're going to see it on our graphing calculator, that stands for standard deviation of the sample. All right, versus this one, this Greek symbol right here, that's going to stand for the sample deviation of the population. I wanted to show this to you because you might see this in your life, but for the most part, we are not going to be using this formula. I do, however, want to talk about what these symbols mean. This symbol right here really means summation, or we're going to sum up a bunch of things. X stands for a value, or basically a data point, if you will. A data point. So it might be your particular score on a test. The X bar, that's how we pronounce it, X bar is the average or the mean. And in this case, it's the mean of the sample. Versus notice here, there's this symbol called mu, and mu actually stands for the mean of the population. Kind of a slight difference, but it makes sense. Next up, we've got N. N stands for the number of items or people in your sample size. And notice how here we actually have a capital N. That's kind of interesting. That N is uppercase because it stands for the number of people or things in your entire population. Again, we're not going to deal with that too much because that's pretty impractical to survey the entire population. All right, let's move forward. I want to go ahead and I want to actually find the standard deviation. Just as a reminder, the standard deviation is kind of telling us how spread the data is. Meaning, do most people score around the same, or is there a huge difference in scores? Like, for example, here you've got a 52 and then you've got a 92. That's a pretty big spread. That's a pretty big difference. We must have a moderately big standard deviation. Versus, let's say I had maybe test scores of 72, 71, 78, 73. That one would have a smaller standard deviation if I use those test scores. All right, let's do it. Again, we are not using this formula. We are going to use this formula because these are just 5 students. These are not the students. This is not the entire world, okay? So again, what does X stand for? That's a value in our data set. So we've got 92, 88, 80, 68, and 52. Well, what is this symbol right here? This is X bar. What is X bar? I have to calculate that. That's going to be my average. So my X bar is going to be adding up all of these values and then dividing by the number of terms. Well, let me add those all up. I get a 380. And I'm going to divide by the number of terms here, in which case is 5. And I'm getting that X bar is 76. And I look back, that makes total sense that that's my average. So in this column right here, I'm going to take my X value to the left and subtract the average. So this is going to give me 92 minus a 76. Okay, moving down, I've got 88 minus a 76. 80 minus 76, 68. Minus 76, 52 minus 76. Well, I go ahead and I do that subtraction, and I'm going to have, in this case, 16, which looks like I'm going to square it. And then here I've got 12, which I'm going to square in a second. 4 squared, negative 8 squared, and negative 24 squared. Now, you might be saying, Ms. Sorensen, why are you squaring it? And the reason is because squaring makes everything positive, and we don't care that something is below or above the average. We just want to know how far away from the average it is. And so squaring gets rid of our negatives and gives us a better understanding of how far away from the average we are. So let me go ahead and do this math here. This is going to be equal to 16 squared is 256, 12 squared is 144, 4 squared is 16, negative 8 squared is 64, and a negative 24 squared is 576. Now, let's go back and let's look at our formula and say, what are they really asking us to do? Well, here, it's asking us to sum up all of these things right here. So I'm going to do that. I'm going to sum up all those values. So adding those all up, that's my calculator, and I get 1056. Sweet. So now let's just go back and plug into the formula. So I've got my S. So my S, or I can write standard deviation if you want. S or SD is totally fine to me. I'm going to have the square root, the sum of all of these, and that's going to be 1056. And I'm going to divide by the number of terms. Well, I've got 1, 2, 3, 4, 5, right? 5 from here, 5 terms right here if I were to count them. I subtract 1 from it, okay, and 5 minus 1 is going to give me a 4. All right, if I go ahead and do that math, I'm going to get 16.25. And what are we talking about here? We're talking about test scores, so this is going to be points. So the standard deviation is, for the most part, test scores are about 16.25 points away from the average. That's a pretty big standard deviation, meaning if I was a teacher, I'd say, wow, my students kind of scored all over the place. So here's a verbal summary of what you need to do. You need to first find X bar, right? That's the average of your sample. And then you need to subtract the mean from each value. So that's going to be that X minus X bar column that we talked about. Then we need to square each deviation from the mean. So that's going to be X minus X bar squared. Then we go ahead and sum up all those values. So if you go back, that was this situation right here. And then I need to divide by the total number of items, n minus 1. In my case, it was 5. 5 minus 1 gave me that 4, and that 4 was represented right here. And then you just finally take the square root of that. So here I am at the very end. You've got my square root right there. Let's do one more, I think. All right, find the standard deviation for this class. I highly recommend you just stopping right now and kind of trying this one on your own and then checking your answer with me. All right, you're back. So I'm just going to go over this problem. I've got 380 divided by 5 gives me an X bar, or an average of my sample, of 76. All right, I'm going to go ahead and drop down these scores: 92, 92, 92, 52, 52. All right, X minus X bar, that's going to give me 92 minus 76, 92 minus 76, 92 minus 76, 52 minus 76, 52 minus 76. That value is going to be here 16, 16, 16. Don't forget to square both of those. And then I'm going to get a negative 24 and a negative 24. All right, doing that math, I get 256 for all three of these. And then I'm going to get a 576. I'm going to sum up all those values, and that gives me a 1920. Okay, what do I do next? I've got the square root of a 1920, Again, I've got 5 terms. Okay, I subtract 1 from that, and that gives me 4. Do that division first, then square root, and I'm left with a 21.91 points. Meaning, compared to the last test, these test scores were even more all over the place. There was a lot bigger difference away from that average. All right. Now, there's a really easy way to find standard deviation on a calculator. I'm going to show you that in a different video, but what I do want to emphasize is this right here. This is where you'll find your standard deviation. Remember, S, that stands for the sample. That is the one we are going to deal with. This one, however, is the population standard deviation. All right, and we are not going to deal with that in this class, although you might in your future. All right, ladies and gentlemen, thank you for joining me on standard deviation, and I look forward to talking with you another time. Make sure you stay quarantined and make sure you stay math happy.